Today we're going to continue on object-oriented programming, finishing up that demonstration that we started last week, but it was a week ago exactly today, on inheritance, because that's what your lab tomorrow is focused on. Remember, just to jog our memory here, remember that we had this scenario where we had a retail store and we had products and subscriptions. And we developed these two objects independently. But we also recognized that there were some similarities between the two. For example, both of them had IDs, both of them had names, and that's the state, the common state, and both of them had functionality of get however much it was. Like with a product, it was the number of things that you're buying, Reese's I think it was, right? Or fudge rounds or whatever. You're going to buy a dozen fudge rounds at 25 cents each, right? So the cost there is $6. But with a subscription, it's different. With a subscription, let's see. Yeah, I don't have anything here. It's going to be a starting date to an end date times your annual fee. So if you started out, at the beginning of the year, you're only going to go till June. At the end of the June, that's only a half a year. You only pay half of that subscription rate, right? So what we did is we redesigned these objects to have a superclass, an item. And then we extended the product and the subscription out so that they were subclasses of this thing. Over here in item, we have the commonality things here, or the common things here, the ID and the name. We also have the common getters and a constructor here. And then we didn't know what to do about cost here yet. All right, so I don't know what to do. I mean, it could be 0. That's a flag value. That's one thing that we could do. But let's go ahead and remind ourselves what's in the product class and what's in the subscription class. Down here in the product class, we override this method. In fact, we can use an annotation here called override to say that we're going to change the behavior that we inherit from my parent up here, from my parent class or the superclass. Instead of returning 0, I'm going to return this product's price times its quantity. Now, if you use this annotation anywhere else, then it will produce a compiler error here because it's going to say that get quantity. Do you see that in your superclass up here? Nope. You're not overriding the method. You can add methods all you want, but you're only overriding if you are changing the behavior of an inherited method. Here we're changing it from computing it 0 to computing this multiplication. Over here in the subscription class, we're changing it so that it's the annual rate times the start date, end date, etc. Right? We also need to continue here. So actually, I'm going to go ahead and get rid of this, and I'm going to go ahead and generate this constructor using fields, and okay, generate them. I shouldn't have deleted that then. Undo, and then okay, I'm going to have to do a couple things here. Generate the constructor using the fields, all of them, yes. Okay, there, that's all I need, right? So now I can get rid of that other one. I should have paid more closer attention there. So let's observe the code that it just generated. To create a subscription, you're going to have to give it an ID, a name, etc., 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 as well as a start date and an end date. Because what we were doing last time when we were trying to compute the cost, remember we got an exception that said, well, this subscription, you didn't specify how much it was and when it started and when it ends, so I don't understand how to create this subscription here. So I've created a new constructor that provides all that information, and so now it should be okay. But notice here what it does. It calls the super constructor. The super constructor item, passing off the commonality to the superclass. Note here that it also calls the superclass. What's the superclass of the item? Do you see that it extends anything? Nope. So it's the object class, right? And that's the end of the road. Java is an object-oriented programming language in that everything is an object or belongs to an object, except for primitive types. Right? But primitive types still belong to an object ultimately. But what's in this object? Nothing. Right? Java is what's called a single inheritance hierarchy. We'll talk about hierarchies here in a moment. But everything derives from object. Everything flows from object. Everything is an object. It is okay. It's equivalent if you say extends object, right? But everything is an object, so don't do that. It's automatic. It's implicit. Okay. All right, so go back over here to demo. Now that I've got my Xbox Live subscription, how much does Xbox Live cost a year? $100? I don't know. 50 bucks? All right. All right. And we'll go ahead and start it at local date of 2022 01 January 1st, and then we'll end it at local date of 2022 6 months in, 30 days at the end of June, right? And now when I run this, I will get an answer, right? I will get an answer of however much this is. How much is it? Purchase total. I guess I'm not printing anything, so let's go ahead and do that now. System.out.println, println, total cost is going to be plus total cost. So how much should that be? 50. Remember, I'm buying these fudge rounds and stuff like that, so there's $12 there, but or candy bar purchase A is going to be what? 2 Reese's at $2 each, so that's $4. Fudge rounds, 12 of them at a quarter, so that's $6. It's $10 plus whatever Xbox Live here. It should be half a year at $50 is 25. So altogether, around 35 or something like that. $31 apparently. Right? I don't know where we're getting that, but you'd have to debug. Right? Okay. Right? This is 1 to 1, and then total. That's half the year, right? Okay. $50 a year. Half the year should only be $25, right? Like we can go ahead and system.out.println. We're in the neighborhood though, at least. I.get cost. So it should be what? What did we say? $4, $8, or oh, okay, that's what. So yeah, it is. It's nearly $25. Why? Because of course there are more days after June, right? 30 days has September, April, June, and November. So, and then of course we're losing 3 in this month alone. So it's a little less than $25, right? Okay. All right. So to review what we just did. All right. Actually, first of all, let me go ahead and go back over here. Let's go ahead and review over here item. Right? So how much does an item cost? $0. What is an item? An item is just an ID and a name. Right? Is it a product? Is it a subscription? Is there really any way that you can compute a cost? No, it's too generic, right? It's too abstract, right? If you get these abstract ideas versus concrete ideas, you can reason about, well, you know, give me a. This actually flows from philosophy. Here's a little bit of a digression. Is there such thing as a perfect circle? Can you, in the real world, can you draw a perfect circle? No. Why? You draw it on the whiteboard or the blackboard, right? What is it? Is it an actual circle? No, it's just if you zoom in on it enough, then you get little flakes of your chalk. Can a computer draw a perfect circle? No. Again, you zoom in on it and it's just going to be a collection of pixels, right? Is there such thing as a perfect circle in the universe? No, there's only the idea of a perfect circle, right? We call those the quintessentials, right? This goes to Plato's Republic. Remember, that's standard reading still, isn't it? Plato's Republic? No? The Allegory of the Cave? Yeah. Right? Yeah. The idea is that we only see shadows of the perfect concepts. That there's this idea of a perfect chair, the quintessential chair. And all the chairs that you see here are just shadows of those things. There's the idea of a perfect circle, but all you ever see are representations of circles. This is the idea of an item, right? It doesn't actually exist. Right? A product exists because it has quantity and it has price. A subscription exists because it has an annual rate and a start date and an end date. But should an item exist? You can't reason about it. So I don't know how to do this, so I'm going to choose to design it so that I don't have to. This is an abstract idea, and so I'm going to make this into an abstract class. Right? Now, I can change this function here, this method, to be an abstract method. I don't know how to implement this, so I'm not going to. All right? Save this. There we go. Then it compiles. All right? So did I provide a body to this method? Nope. This is very similar to what you see in C. What do you see in C if you don't write the method body? These are called what? The declaration, it's a prototype, right? It just says that there is this function out there called getCost. Oh, great. What does it do? I don't know. I'm just an item, right? What does it do? Product. Oh, I take my price and I multiply it by the quantity. Oh, what does it do? Subscription. I take my annual rate and multiply it by the period here, right? Yeah.
So if you don't have the getCost in the item, it will go down to the price?
No, it will not. In fact, let's go ahead and get rid of this. Now, product over here is complaining because, hey, you said that I inherit and change this method, but there is no getCost method in the superclass anymore. Right? So, let me restore that. The reason that you would want to do this, again, if you go over here to the demo, is that you can treat all items the same. Right? You can put, if you didn't do this, you'd have to come up with at least 2 receipts. I'll list all of your products. I will list all of your subscriptions. And then I'll have a total, right? I'd have to have 2 loops here to do a total instead of just 1 loop. Well, now think ahead. You think of a new product, like a gift card, or another new product where the cost is computed differently, right? Another new product, another new product. At some point you have 10 classes, right? And are you going to have 10 loops to do the same thing of just summing up the total? No. Treat them all as one idea. Everything has a getCost method that returns a double that you can then add up, and you can use inheritance to do that, to unify them. Right? All right, so let's come back over here to the demo. Another consequence of making something abstract is that you can't create it anymore. Some item is equal to new item. Even if I give it a proper ID, foo, and something, right? I'm not allowed to do this. It's an abstract idea. If you actually created an instance of this, you wouldn't have an abstraction. You would have a, what's the antonym of abstract? We decided this morning it was concrete, right? You'd have a concrete thing that you can hold in your hands, right? So because it is an abstract idea, because it's an abstract class, you're no longer allowed to create this thing, which is probably a good thing, right? There's no such thing as a generic abstract item that you can actually put into a receipt, right? It's got to have a price. Otherwise, you can't put it into a receipt. Okay? All right, so let's go over what we just did. In Java or any object-oriented programming language, you can create, or you can, in Java in particular, if, I'm going to rephrase this, if a class A extends, and that is the keyword, that's why I'm putting it into a code mode there, extends class B, then A is the subclass, B is the superclass. Another way of putting this is that A is the child class and B is the parent class. You can also say derived class. You can say extended class. You can say a bunch of different things. You can come up with all this different language. I'm just going to use these two. Superclass, subclass. Parent, child, just like a parent-child relationship in a database or a parent-child relationship in a family tree, right? It grows down and it forms what's called an is-a relationship. Inheritance forms an is-a relationship, right? In this case, what did we have? A product is an item. A product is a item. Right? What else is an item? A subscription is a item. Right? So you can treat it like an item. But I'll ask you this. Is an item necessarily a product? Does it work both ways? No, not necessarily, right? Is a product a subscription? How about that? Nope. This relationship, these three different relationships, are what's called covariance, contravariance, and invariance. Now, to understand this, let's go ahead and look at something simpler, right? Something not contrived and related to an online store here. Instead, let's go ahead and go with a bird, right? Very similar inheritance hierarchy here that I created. There's an abstract notion of a bird. All birds move. All birds speak. But the way they do it is different. For example, a robin. A robin is a bird, right? How does a robin move? It flies. How does a robin speak? Tweets, chirps. Well, the way that I designed it here was what? It overrides the moving method to fly, and it overrides the speak method to tweet. Now, a different bird, an ostrich. An ostrich doesn't fly, in case you didn't know. Right? They're too big and tasty. Right? You can't get yourself an ostrich burger if you go down to a Fuddruckers. Right? And they don't they don't sing nicely. It's rather screechy honk, I think. Right? You look up some YouTube videos and ostriches speaking of some sort. So it says honk here. Okay. These are specializations. Right? All birds move somehow. But we don't know how, so therefore we can't create a generic bird, right? But in the subclasses, when they extend a bird, a robin is a bird. Right? But is a bird necessarily a robin? No. An ostrich is a bird, but a bird is not necessarily an ostrich. And what about these two taken together? Is a robin ever an ostrich, and is an ostrich ever a robin? Nope. That gives us these relationships here. Right? So up here I have the superclass. Down here I've got these two subclasses. A covariance is where you're taking a subclass and treating it like its superclass. And that's always fine because it forms an is a relationship. A robin is a bird. An ostrich is a bird. Right? That's always going to be safe and perfectly valid. Right? That's the whole point of doing inheritance. But what about a contravariance? What happens when you take a superclass and you try to force it to become a subclass? If it were an ostrich to begin with, that's fine. But can you take a robin, treat it like a generic bird, and then force it to become an ostrich? No. That's contravariance. Sometimes it's safe. You have to check. Right? But can you ever take a robin and force it to become an ostrich? No. That's called an invariance. Right? That's never safe. So, always safe, always fine. Sometimes safe, sometimes not. Never safe for invariance. Okay? Let's take a look at a demonstration that I've got here, bird demo. Right? And let me go ahead and roll this all back. Ignore it, ignore, ignore. There we go. All right. So, is it possible to create a new bird? What kind of bird is it? Who knows? That's why it's not possible, because I made it abstract. Right? I can create a new ostrich. I can create another ostrich, but treat it like its generic parent class bird. Right? We do this all the time. Remember when we created lists? There's a list data structure, and we created a new array list. That's inheritance right there. An array list is a list, as we'll see here shortly. Right? I'm treating it like it's super type, which is always fine, because all birds move, all birds speak, right? Somehow. I can create another bird, which is a robin in this case. So let's understand what happens when I call all of these methods. When I say o.move and o.speak, it should be obvious that that's going to be walking and honking. Right, there we go, honk. Right? Why? Because it's an ostrich. But what happens when I change it to B1? Well, that's also an ostrich, even though I'm referring to it as a bird. Right? So, same thing. Right? But what happens when I take something that is a bird, but it just happens to be a robin? That's going to end up being flying and tweet. Later on, I can create another bird reference, say B3 is equal to, I can point it to B2 and make it speak, move and speak. There we go. And this is a circuitous reference, so B3 is referencing B2, B2 is a robin. How do we know that at this point, at this line? Do we have any idea what it is? Nope. We just know that it's a bird, that it can speak and it can move. I don't know how until you invoke those methods. Right? And it's flying tweet. You could also make it point to B1, in which case it will be walking and honk. Right? The way this is achieved is through what's called a virtual table. And I'll show it to you really quick here. It's not exactly a one-to-one thing here, but when a robin is created, all of its attributes are put into one table. When an ostrich is created, all of its attributes are put into a table somewhere in memory. That table doesn't actually have the code to move. Instead, it references some other code that prints out flying. Likewise, the ostrich is referring to some other piece of code that says walking or something like that. These are called virtual tables. And they're created when you instantiate a new object, when you say the new keyword. And you can't, generally, you can't redefine what these are pointing to. That's how it knows, well, how do I call this move method? If I just follow that code, it just takes me to the abstract method. But when it gets compiled and run, it will actually instantiate it to one of these move method, this move method or this move method over here. It's a runtime thing. It's called dynamic dispatch. Which what method are we actually going to call? I'll look it up in the virtual table and call that method at runtime. Yeah?
So when you said it equal to either robin or ostrich, is it a shallow copy or deep?
That's a shallow copy, yeah. It's just a reference copy. Okay. Now, let's see those covariant, contravariant, and invariant in action. We've already seen covariance, right? I can take an ostrich and treat it like a bird. I can take a robin and treat it like a bird. Let's try contravariance, or invariance, first of all, because that should be obvious. Can I take a robin, R, and what is my ostrich, O, and make it refer to O? Remember, O is my ostrich right here. It's not even going to let me compile this. Why? Type mismatch. Cannot convert from ostrich to robin. Okay, I really want to force it to. How can I force a variable to become another variable? How can I force an integer to become a double for the purposes of division? Cascade. Okay, fine. Compiler, I forget you. I'm going to force this to become an ostrich. Well, it still can't. I can, however, force a bird, say B1, to become a robin. Right? The compiler doesn't see this. Why? What is B1 as far as the compiler is concerned? It's a bird, right? So in this case, contravariance, but is it a safe contravariance? Nope, because I took an ostrich, treated it like a bird, and I'm forcing it to become a robin. Right? And what happens at runtime, we'll see. Class cast exception. Right? That's an invariance. So that's not safe. Let's look before we leap. Now, do not do this under most circumstances. I'll tell you the circumstances in which you can do this in a moment here. But you can use this instance of keyword. Right? So is it safe to force B1 to become a robin? If B1 is an instance of all one word, robin, then this would be safe. Right? I'll even say system.out.println safe. Right? Else, I'll say that this is an invariance. Not safe. What's the opposite of not safe? Unsafe. we start in 3 days. Thankfully, the long winter is over. Out. Oh, nobody follows baseball apparently. We may not even have an MLB season, unfortunately, because of the lockout. But college is safe. Nobody follows. Oh, come on. We had an excellent team last year. Hopefully they'll do just as well this year. All right, anyway. So, is it safe or not? Out. It's not safe. Oh, here. Not safe. Out. Why is that not safe? Because it was not a robin, right? It went into its virtual table, its V table, and said, wait a second, this is not a robin. This is an ostrich, right? And this evaluated to false, giving me this printout right here. But is it okay to force a, let's see, if it's an instance of a robin, B2, right? And B2 right here. Right? Can I force B2 to become a robin again? Yeah, because I looked before I leaped, right? It's safe because B2 is an instance of a robin. You can see it right here, right? Do not do this in general. For example, if you did this to compute your, let's see, go over here, to compute your cost, right? If you said, if, here, I'll take it inside the loop here, sorry. If I is an instance of product, then do one thing, right? Else if I instance of, is it? No, it is case sensitive. Subscription, do something else, ... right? Code completion, haha, right? If you do something like this, you are completely breaking encapsulation. You are completely breaking inheritance, right? There's really no point in doing object-oriented programming if you're going to be doing this. Because again, if you have 10 different products, what do you have? If this, 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 right? You're locating all of your business logic outside the class. How do we compute the cost of a product? You multiply the quantity times the price. That sounds like a product thing. If it's a product thing, where does it belong? In the product class. If you're computing the number of days between two dates and multiplying by an annual fee, that's a subscription thing. Where does it belong? In the subscription class. It doesn't belong here in the demo class. There was a question? Okay. The one instance in which you can probably forgive yourself for doing something like this is when it's absolutely necessary. If you need to create, say, a new product copy is equal to new product, you have to force I to become a product in order to call the appropriate constructor, ... Right? If you're going to call a copy constructor, you have to know, what is this thing? Oh, it's a product? I'll call the product class's copy constructor. Oh, it's a subscription? I'll call the subscription class's constructor. That's the only time that you can do that. Yeah?
You just make a copy of an item, or you can just make the copy.
Remember that we made item into an abstract class, so we can't even create it, right? If you wanted to, it was a design choice to make it abstract, right? I wanted to prevent somebody from creating a generic item because if it appears on a receipt, what's going to happen? I don't know how to compute the cost, or it ends up being 0, or some even worse flag value like null, and then it's a null pointer exception, which has nothing to do with it, or it's a -1, which now okay, that's a discount then, right? I get $1 off just because somebody didn't know how to program, right? All right, there we go. All right. So, covariant, contravariant, and invariant coercion types or relationships. All right. So let's see. Inheritance is achieved at runtime by building what are called virtual tables. Right? The methods and state for a particular object are created at instantiation, right? That is the new keyword, and stored in a V table, right? When calling an object's methods or accessing its state, a dynamic dispatch is used to look up the appropriate method in the V table and execute its code. And that's how it ends up working behind the scenes. One of the very first object-oriented programming languages, C++, was actually just a thin wrapper around C. It took all the object-orientedness, like this virtual table and stuff like that, and it achieved it through function pointers. So it's, in some sense, the entire paradigm of object-oriented programming is nothing more than a bunch of really, really sophisticated syntactic sugar when it gets down to it, right? At the end of the day, it's still referencing something like this virtual table, and this is a reference, a function pointer to another function, right? Call that function over there, or call that function over there. And it's all called dynamic dispatch. Why dynamic? Because it happens at runtime. If it happened at compile time, it would be static dispatch. Static, dynamic. Static before compilation, dynamic after compilation. Okay? So again, why do we do all of this? The advantages. We like organization. So does anybody remember the mnemonic device for kingdom, phylum, class, King Philip, something, something, something? No? Nobody in the morning section knew either. King Philip, kingdom, phylum. What is it? Mnemonic update. Oh. So, come on, what is it?
Over for good spaghetti.
Came over for good spaghetti. There we go. Right? Oh, it's domain. Dear King Philip came over for good spaghetti. There we go. Domain, kingdom, phylum, class, order, family, genus, species. Why do we do that in nature? Why do we do that in biology? Organization, exactly. Right? If you looked at all the possible organisms on this planet, all billions of different species, right? It would just be one big mess. So what we do is we organize them into a hierarchy to make sense of it. We can talk about all mammals, or we can talk about all viruses, or we can talk about all plants. Then you can get down to more specific things. Talk about all hominids, right? And then get down to one specific species, right? Humans, etc., right? We like organization, and a hierarchy is a natural organized structure. Right? And that's why we like inheritance. We like code reuse and reduction of redundancy. If I have two very related objects that both have the same state and some common state, like an ID and a name, and some common behavior, like getting cost, put that stuff into one common class and create an inheritance. Right? We like code reuse and the reduction of redundancy. Right? Those are both advantages, and also subtype polymorphism. Right? We'll talk about that later, though. Right? You've seen a preview of it. Did I have to create a list of subscriptions and a separate list of products, and then later on a separate list of gift cards, and later on a separate list of whatever, whatever, whatever? No. I created one list of the super type so that I could collect them all into one list and only have to have one piece of code that iterated over them to generate a total. Right? And that's only possible if you use subtype polymorphism. Treating all these subtypes as their super types so that you can do one operation on any list of any type. Right? Write one piece of code to apply to multiple pieces, to multiple types. Okay? All right, so some other miscellaneous stuff. Miscellaneous. Right? Sometimes you don't want to allow someone to subclass your class. Right? You can make it final to prevent them. Right? Remember, by subclassing, we're changing behavior. In the item class, we changed it so that instead of returning 0, in the product class, we multiplied quantity times price. Right? Think about another common class integer, right? X. Should you be able to change what an integer is? I'll subclass integer to be my special integer, and I'll do something wacky like change multiplication into division, or change subtraction into plus, right? That would completely go against everything that you understand about how integers work, right? Or I would change it so that I would throw an exception if anybody ever tries to set it to 0 or something, right? Some really weird, wacky kind of stuff. There are certain types that have a built-in understanding of what this thing is. And you shouldn't go mucking with that. You shouldn't go be changing the program. And so consequently, can you change integer? Nope. We made it final. Where else have we seen the final keyword? Constants. It changes a variable into a constant. You can't change it. It changes a class into a final class. You can't subclass it. Right? Now, if you want a little bit more fine-grainedness, you can do that on the method level. Making a method final makes it non-virtual, right? And you cannot override it in any subclass. Right? That's the buck stops there, right? It's just it's the opposite of this virtual table lookup. It means that you will not be able to redefine it so that it points somewhere else. If you make a method final, you can still subclass the class, but you can't override that one method. Right? By default, everything is a virtual method. By default, in Java, all methods are virtual. You make them non-virtual with the final keyword. In contrast, C++, all methods are non-virtual. You must make them virtual using the keyword, I'll let you guess. It's not the opposite of final. I don't know, what's the opposite of final? Non-final. Beginning, I don't know. Anyway, they use the keyword virtual. Right? That thing is virtual over there. You can override it, but by default, they shut it off. Right? That was just a different design choice as far as the language folks go. Right? I don't know what it is in say. I think most languages, all methods are virtual by default unless you make them non-virtual. C++ is kind of a different one like that. Right? You can make a class. We already covered this, but I'll put it in the notes here. Abstract, right? And it may have abstract methods. Right? An abstract class cannot be instantiated. You can't create instances of an abstract class, and abstract methods have no body, right? Right? No body, no definition, right? And consequently, in any non-abstract subclass, you must provide a definition or implementation. Right? Otherwise, you can have a chain of abstract class, abstract class, abstract class, abstract class. In fact, let's take a look at one that you might be familiar with already. This big giant inheritance hierarchy for the collections hierarchy. Here we go. Bring it over here and zoom in. Right? So we have a hierarchy here of the tree sets, hash sets, array lists, and linked lists. You've probably looked at both of these here, a hash set and an array list, right? When you create a set, you actually create a hash set. When you create a list, you've probably created array lists. All of these things are collections. All of them are iterable. They all inherit from abstract collection. Right? We have this kind of hierarchy of more concrete down here, less concrete or more abstract up here, until you get to these things called interfaces. And interfaces are pure abstractions. They are classes where all of the methods are abstract and there's no definition at all. Right? So that's our next thing. An interface is a pure abstract class, right? It may have state, but usually doesn't. In fact, I won't even mention that. All of its methods are abstract. Now, I will say verbally here, there's an asterisk there. In a later version of Java, they defined what were, they added a feature called default methods. For all intents and purposes, ignore it. Right? They basically made it so that we've got these great things called abstract interfaces, which are purely abstract classes. You know what? Instead of just having 3 layers, we need a 4th layer in there somewhere. So in between abstract classes and interfaces, they added default methods, which basically took interfaces and allowed you to have a default method so that you didn't have to provide one. In some very limited use cases, it is useful, but in the vast majority of them, it's not. All right, so don't worry about it. For all intents and purposes, we still only have these 3 layers here. Right? And why would you want to do something like this? Right? Why do we need 3 layers? Right? In Java is a single inheritance hierarchy. You can only extend one class. Right? I can't extend multiple classes. For example, let's go ahead and close this. We'll make an ostrich extend bird and subscription. Right? So an ostrich is a subscription. You get a subscription to an ostrich. Well, I guess if you want to go to Fuddruckers, you can subscribe to an ostrich burger or something like that. But you can't do something like this. Right? You can, however, do it with interfaces. Right? Let's go over here. Take a look at an array list here. An array list only inherits from one actual class, in this case, an abstract class. But it can implement multiple interfaces. In particular, it implements serializable, clonable, random access. What else? Is that it? Just 3? Yeah, at least for this one. These 3 up here, right? Now, why would you want to do that? When you get down into abstract classes, an actual inheritance hierarchy, you are locked in. That's it. If you start to move things around later because you feel that, oh, this is not the correct model here, I need to move this over here or move that over there, everything below it breaks, right? Because it is all built, it's all a bunch of dominoes built on top of each other, but it's growing down, right? You remove one of those dominoes, the entire hierarchy below it breaks. Everything above it is perfectly fine, right? But everything below it breaks. So in some sense, it's better if you want to keep things abstract so that you're not locked into this hierarchy. And in that way, you can actually implement multiple interfaces. For example, serializable simply means that you've got this method that can write it out to and read it from a bunch of bytes, so that you can take it from take this class, this instance, from one instance of a Java virtual machine, send it over the wire to a different Java virtual machine sitting on a server somewhere, and those Java virtual machines can speak to each other in binary. It's only you can do that if it's serializable. You're doing that right now, but not in Java binary. You're doing it with CSV2, remind me? XML and JSON, right? That's serialization. It's just a different format. Random access means that you can jump to a location for free, right? An array list can do that because you've got an array. If you want the 5th element, right, then that's at index 4. That's just 4 times as many bytes and then jump to that memory location. That's what random access means. Does a linked list have random access though? Nope. So it would be inappropriate to make it that all lists had random access, but if you leave it out here as an interface, then it doesn't lock you into this hierarchy, right? And that's why you might want to use an interface in some instances. All right. Java is a single inheritance hierarchy. You can only extend one class. In general, a hierarchy locks you in to that design. Right? It is not easy to change. Right? However, you can implements, bad grammar, but that's the key word. You can implement multiple interfaces with no problem. Why? because it only defines that you have these methods. It doesn't actually define what those methods are. You're not inheriting the behavior. You're just inheriting the signature of the function, right? Cool. In fact, some of these don't even have functions at all. They are pure ideas. Random access, that interface doesn't define anything, right? It's just a semantic idea that yes, you can go ahead and use random access on this data object. We'll see later on why that matters. In fact, we can look it up. I'll show you. It doesn't do anything. It doesn't define anything. Random access interface Java. Right? Random access right there. What are the methods? There are none. It's just informational. It's telling you something about this object. Right? There are no methods at all. Cool. Right? But you're only able to do that if you can mix. Sometimes these are called mix-ins. In real life, what's a mix-in? Oh, nobody goes to, not Baskin Robbins. What is the Cold Stone? Cold Stone. You get some ice cream. What do? Do you just get the ice cream? No. What do you get? The toppings, and those are called mix-ins, right? So you can mix it in. If you're creating an object, you can mix something in by adding that interface, mix in that interface, mix in that interface. Right? Oh, I didn't mean to do that. You can always take it out. Right? You can't do that with your ice cream, but you can order a new ice cream. Yeah.
So for the interfaces, do we extend them? Or
Nope, you implement them. And again, that bad grammar, but that's what the key word is.
where does that go in the actual program?
Good question. So here's another example. And this is kind of similar to what you're going to be doing tomorrow in your lab. Here's a hierarchy for a payroll system. This payroll system has interns, employees, and suppliers. But at this particular company, interns are not paid. Right? So if I lock them into an employee hierarchy, I would be forced to return 0, right? Whereas if I put them into an interface here, payable, I pay my employees, which are hourly and salaried employees, but I don't pay my interns. Right? They're unpaid interns, right? But an intern is a person, and an employee is a person. But I've also got this concept of the supplier over here, right? They supply me with raw materials or whatever, and I do have to pay them, right, for their services. But they're not necessarily a person. It's just another company, right? So if I've got this kind of model and this kind of setup, I'm only able to do this if I've got interfaces. Employee implements person and it implements payable. But an intern only implements person, right, and not payable. And a supplier implements only payable but not person. And down here, an employee inherits both the person and payable. An employee is a person who is payable, and therefore an hourly employee is an employee. Remember, this is a relationship all the way up, who is a person and that who is payable. And so this kind of hierarchy is a perfect use case for when you would want to use a variety of these things. Right? Syntactically, what does it look like? If that was the original question, give me something else a bird does. Eats. Okay. No, eatable. Edible. Okay. Oh yeah, you're right. Eatable. There we go. There's my interface, right? Usually, it's difficult because the pattern you follow is this is not a verb, it's an adverb, right? Interfaces are adverbs, right? And so I don't know how to say this, but public void eats, right? I don't know, eats maybe more appropriate. I don't know. I'll just go ahead and leave it like this. And then over here, a bird would implement, a robin, say, eats, implements, eats, eatable, right? Now it's going to complain until I add that implemented method of eats. What does a robin eat? System.out.println, eating a worm. And I have no idea what an ostrich eats. Feed? Eating a seed? Something like that. and they implement eatable. Right, there we go. Or I could take this and put it all the way up into the superclass, and then I don't have to put it in both subclasses. Right? It's way more flexible because I can pick and choose. I can pick and choose. I can mix in here, or I can mix in here, mix in here. That's why we call them sometimes mix-ins. Right? Okay? With no problem, right? Often you do this to leave your hierarchy flexible and use mix-ins, right? Okay. Let's see what else. Final, abstract, interface, pure abstraction. Okay, we might come back around to other things here, but let's talk about pitfalls, right? Some languages support what is called multiple inheritance. Exactly the opposite of what I was just talking about, where instead of inheriting from multiple interfaces, you can actually inherit from multiple classes. Now this is a contrived example, but it's a perfect example of illustrating why this is a pitfall. Right? So suppose that I've got a dog, a cat, and are both animals. Right? So I've got an animal, a dog, and a cat. Now, for whatever reason, for whatever crazy reason, suppose I create I don't even know what to call it yet, we'll give it a name here, class that inherits from both dog and cat. What is it called? Maybe I always date myself when I get to this point because I always use the same example. And nobody's ever seen, again, everybody's too young. There was at least one person that remembered it. Cat dog, right? Cat dog. There's a cartoon called Cat Dog. What did it look like? It was a cat on one end and the dog on the other end, right? It was just a weird cartoon. I just remember it, but I didn't actually watch it, right? I watched plenty of other cartoons though, right? So we've got a cat dog here. The problem is there's an ambiguity. Suppose that it has a method called eat or speak. That's easier. A dog barks, a cat meows. So what does a cat dog do when it speaks? Yeah, exactly. It's an ambiguity. Does it inherit from cat or dog? Now C++ does support this. The way that C++ gets around this is it says you have to explicitly state that when you inherit from or when you come from two different classes, what about the speak method? Are you inheriting from the cat or are you inheriting from the dog? Or are you doing something completely different? This is known as the diamond problem. Right? Why is it called the diamond problem? I don't have an easy way of drawing this, but imagine here. Up at the top we've got animal. Then I've got cat dog, or cat and dog independently. Then they meet together down here as a cat dog. What did I just draw? A diamond, right? And it's an ambiguity, right? That you don't know where the inheritance comes from without reading the documentation. So you actually have to read the code or read the documentation to find out what the hell is going on here. Right? You don't have that problem with Java because Java prevents this because it's single inheritance. In Java, no problem. Single inheritance only. Right? Now they screwed that up when they added the default methods I was talking about before that I told you ignore that they exist. So a problem that they solved, they decided to make it a problem again later on, right? By reintroducing it, just for reasons apparently. Okay. You also have another these are called anti-patterns. Do you remember? I think we talked about the God anti-pattern, the God class, right? You take everything and put it into one class, right? That breaks encapsulation. That breaks abstraction. If it's an address stuff, then you put it in the address class. If it's a person stuff, you put it in the person class. That's an anti-pattern, a bad behavior, right? Not as opposed to patterns, which are good behaviors. There's one anti-pattern called the yo-yo problem, or yo-yo anti-pattern. So in general, keep your inheritance hierarchy shallow. Right? This looks a little bit complex, but it's not that deep. Right? If you only consider the actual classes here, it's only 4 levels deep. 5 levels deep, 6 levels deep, maybe. But if you're getting to 7, 8, 9, 10, 20 levels deep, right? Then understanding this means that you're going to have to look all the way to the top. Right? Okay, I see that attribute up there. Where did it stop? Or where was it introduced? Where was an attribute introduced? I'll start at the bottom. Okay, there it is, right? Where was this other thing? Okay, I've got to go all the way up there. Okay, now I need something more specific, so going down. What are you doing with your head looking at the hierarchy? You're looking up and down like you're watching a yo-yo, right? Go up and down. And that's why it's called the yo-yo anti-pattern, right? In general, you want to keep your hierarchy shallow and simple, right? And again, the reason is that once created, you are pretty much locked into that hierarchy, right? And there are bad hierarchies that we've had to deal with in Java. This is not one of them. It was well thought out. But do you see maps in here at all? No. Is a map a list? No, that doesn't sound right. Is a list a map? That doesn't sound right either. One holds things in an ordered manner, and one holds things using a key value pairing system. Is a map a set? Not really. It has a key set. It's part of it, but it's not really. But it is. Is it a set? No. Is a set a map? No. So instead, rather than locking it into this hierarchy where none of that really made any sense, it's over here by itself. Right? There's a separate hierarchy. Right? Now, at the end of the day, everything goes all the way back up to object. Right? It's a single inheritance hierarchy, but again, once it's created, you're locked in there. So it better be a good design up front. The last one is a rectangle problem. Right? All right, so suppose we have a shape, square, and rectangle that we want to represent here. So a square and a rectangle, those are both shapes, right? What about the square and rectangle? Is a square a rectangle? Technically. Is a rectangle a square, though? No. So what if we decided that we wanted to model this? Can I close all? Yeah. Model this using classes. Eatable. Let's open up rectangle, square, and shape. So here's shape. It's abstract because it could be a circle, it could be a polygon, it could be anything. But I also have a get area here, right? So it's a 2D shape. Right? Now, a rectangle is a shape that has a width and a height. If we went with the idea that a square is a rectangle, then that puts me into this three class hierarchy: shape, rectangle, square. But now let's look at this demo here. I create a square, and how big is it? 10 by 10, right? So 100 feet. Later on, I reset its height. Is it a square anymore, semantically? No, it's 5 by 10, right? Now it's a rectangle. But what's its type? It's still a square. In fact, instance of square will tell you that I'm still a square, even though I'm only now 50 feet of area. I'm a 5 by 10 square now, right? Yeah. So does this hierarchy make sense? No. One solution would be don't allow that, right? Throw an exception, or better yet, make it. Where's rectangle? There we go. Make them final, and now it's immutable. Once you create it, you can't change it. That sounds a little bit better, right? Third solution, don't do this at all, right? That hierarchy doesn't make that much sense, right? Yeah, it makes sense from one point of view, but again, you're locking yourself into this thing. This is a violation of what's called the Liskov substitution principle. Barbara Liskov, it's part of the solid principles that we'll talk about later on after we've had a chance to look at polymorphism. Right? So, yeah, don't do something like this to begin with. Right? Changes can change an instance's properties, but the type cannot change. Right? This is a violation of the Liskov substitution principle. Right? The Liskov substitution principle simply says that if you've got a subclass, you can always treat it like a superclass. But can you always treat a square as a rectangle if you allow its dimensions to be changed? No. Right? Another even worse solution would be anytime you do change the width, change the height. That's called a side effect, right? And that's even less desirable because now I just said that I wanted to change the width. Why are you changing the height on me? That was unexpected, right? And it's magic going on behind the scenes to ensure that you're still following the Liskov substitution principle, but I don't tell you anything about it unless you read the documentation. Right? Or worse that, you have to actually dive into the code. Right? So avoid that. Those are the common anti-patterns. Okay. So with the last few minutes here, tell me, you've already looked at, you're already working on, by the way, we're not expecting any inheritance on your first phase. If you want to, go ahead and develop some inheritance. We'll tell you if it's good or bad. We will not grade you on it until phase 2. Phase 2 definitely has got to be there. But you know, start thinking about what entities are related and how they're related, right? In your project, I think we've got what? Cryptocurrencies, stocks, properties, right? What's a commonality between all these three? Yeah, so probably screaming out to you to do something with that, right? Probably some sort of an inheritance. But that's inheritance. Do I have any more nice diagrams here? Nope. That's all of them. Here's a simplified version of the inheritance hierarchy for a collection, right? A hash set is a set. A set is a collection. A collection is not necessarily a set or a list, right? It always goes upwards. Is a. And you can always treat a set like a collection. You can treat a list like a collection, but you can't necessarily treat a collection like a set. Right? Can you sort lists? Yep. Why? Because it holds things in an orderable manner. Can you sort sets? No, because there is no ordering on it. Right? So what does a sort look like? It probably operates on some sort of a list, right? A list interface. Right? I think that's it. If you wanted to see, okay, give me something else a bird does, and I'll show you how to implement multiple interfaces. Nestable. All right, there we go. Public, void, make nest, nest. There we go. And then we can make a bird, implement eatable, and I think it's, there we go, oops, nestable. Nope, that's not it. It is a comma. There we go. Comma delimited list. But you can't say that let's go down to Robin here. And you can't say that it extends bird and it extends ostrich. Right? You can't do that. It's complaining about other things here though too. So let's get rid of that, fix those other things. The only thing that's complaining about here is that it's nestable, so you have to add that make nest and then do something with it. But you certainly cannot extend two things like, say, square. Right? A robin is a bird and a square. You can't do that. Single inheritance hierarchy only. Okay. All right, well, that was much tighter than this morning. Yeah, I can't think of anything else. One other thing, there has been a thread on Piazza on Lab 5. We give you this image. This is called a UML diagram, and this is the inheritance that we're expecting out of an employee, hourly employee, salaried employee, temporary, and staff in hourly employee. And then we've got this payable interface up here for a supplier and an employee, and a couple of other things. This is UML is a universal modeling language. It's an actual language that you can use to generate diagrams, not just with classes and stuff like this, but with anything, with flow diagrams and other things. Unfortunately, what I used to generate this was called Object Aid, and it's now been, or somebody didn't pay their bills, and their website is down. And I have sent an email to the creator to see if he actually exists anymore, or maybe they're just retired or something like that. But one workaround that I tried was going to the Internet Archive, web.archive.org, and I went back a couple of years and got the zip file that was on their website. I did install it. Unfortunately, it doesn't work because if you try to create a new, it installs fine. New other object aid class diagram foo. It doesn't let you finish. There's something wrong in the background. One post said that it works on Eclipse 4.19 and previous. This is 4.21. So if you've got an older version of Eclipse, it'll work. If you go and get a separate older version of Eclipse, it'll work. I've tried at least a half a dozen alternatives. One of them is, what is this called again? Papyrus. I couldn't get it to work. If somebody does, post some instructions. Another one that I tried was this one, but it's paid. But if you're a student or an instructor, you can get a free license. And that was okay, but you have to jump through like a half a dozen hoops to actually install this thing. It was Yatta, I think it was. Signed in at Yatta. Yeah, there we go. YATTA. So if anybody finds a UML diagram generator that automatically generates this, by the way, I didn't draw this. All I did was drag a bunch of classes onto this tool, and it automatically generated it for me. And that's what I recommend that you do. But if worse comes to shove, or worse comes to worse, you can always draw UML online. You can always go with a tool like this, Visual Paradigm. Jump down to the bottom here. There should be a Get Started. Where's Get Started? All right. In order to save it, you probably will want to sign up. It is free, and log in so that you can actually save these things. Otherwise, I guess here, go to the beginning, and there you can get started. Start creating. Diagram, class diagram, just create blank. And then you can draw it this way and then export it as a PNG. There's a class. There's another class. And how do you make a connection back and forth, an arrow, and then you'll want to do something like that, right? And then move things around, right? So it's not great. It's not automatic. You do have to draw it. I would suggest that if you're going to do something like this, that you do save it, because you're probably going to want to make changes ultimately, right? And if anybody finds a really cool, kick-ass version of this, let the rest of us know. All right? Yeah.
This is basically a mind match.
I mean, it's a way of visualizing stuff. So at the end of the day, what is everything? Everything's a graph. So a mind map is a graph. UML diagrams are maps. ER diagrams are maps, or graphs, excuse me, graphs. Right? Why? Because you have nodes, vertices, and you have relationships between them. Right? So at the end of the day, everything is a graph.
It's a subclass.
Yeah, yeah, it's a special type of graph, a subclass of graphs, right? So, yeah, your mileage may vary. Again, let us know if you find a really cool one. Okay? Or you can always draw it by hand if you really want to.